Any question if you have?
Yes.
Hmm.
Sir, in comparison to the poor continental areas, coastal areas, and the surface of the oceanic areas are due to we have more fog or smoke. So fog and smoke brings more pollution towards the surface.
Not necessarily. When we talk about first, what is fog? Fog is the condensed water droplets. We haven't discussed that yesterday also. Yesterday that was a passing reference with respect to temperature inversion. Once we understand the relative humidity and the precipitation and how the condensation will take place, hopefully that will not be a query. First, for the condensation to take place, moisture in the air must be there, right? So any water body, the air above the water body will contain more amount of moisture. Hence, those areas will be more vulnerable for fog as compared to the continental area. That's why oceanic areas will have greater fog. When we compare with urban areas and rural areas, urban areas will have greater fog, and so on, right? Atmospheric pressure. If you look at atmospheric pressure, we have basically pressure is associated with weight. Anything which has weight can exert pressure, right? What is the definition of pressure? Normal force per unit area, and that force can be exerted by weight also and by dynamism also, by movement of something. If anything is moving, right, that can have its impact over pressure as well, right? So since atmosphere do have weight, if you look at atmosphere do have some weight, so because of the atmospheric weight, the pressure exerted upon the ground is called atmospheric pressure, right? And average atmospheric pressure on the ground is roughly around 1013 millibar, millibar being the unit of that, right? And this is an average pressure. When we talk about average pressure, that means there is not uniformity in it, and there is imbalance in pressure system in different parts of the earth, right? So we may have two sets of pressure, that is high pressure and low pressure. Now, if you look at high pressure and low pressure, that is very relative term. High pressure is the pressure of an area. If it is more than the surrounding area, we'll call it high pressure. And if the pressure of any area is less as compared to surrounding area, it will be low pressure, as simple as that. There is no fixed quantity or fixed measurement for pressure system when we define high and low, right? Let's say suppose in the case of atmosphere, if we take an example through number of air particles, if the number of air particles per unit area is heavily concentrated, in any parcel of air, let's say suppose this, and if it is relatively lesser, I'm talking about the same adjacent area. If it is scattered, air particle is relatively scattered, right? In the case of atmospheric parlance, when the concentration of air particle is more, it will generate a high pressure area and it will generate a low pressure area, right? So it is all about the number of particles present per unit area in a region. that will determine whether it is a high pressure area or low pressure area. The moment there is a pressure variation in the region, the air will start flowing from high towards low pressure, right? This is what you call gradient. Just like the temperature gradient, we have pressure gradient as well. What is gradient? Difference in the number of air particles with per unit area, right? Difference in number of particles per unit area. Atmospheric particles per unit area, right? Adjacently, if it is decreasing, that means we are moving from high to low. If it is increasing, we are moving from low to high. And air will always move from high to low pressure area, right? Now, in the atmospheric circumstances, if in the atmospheric condition, what are the factors which will create pressure? First, we'll try to look into the relationship between pressure and temperature. We have already dealt with that. So, how pressure is related with temperature? In an open air system, it will be inversely proportional, whereas in the closed area, it will be directly proportional. So, atmosphere is an open system, so it will be inversely proportional. That means high temperature will produce low pressure, and low temperature will produce high pressure. Since the temperature distribution varies on the ground, there will be variation in pressure also accordingly, right? Now, the simple rule, how the low pressure and high pressure will behave. We can have an example of, let's say, a heater. If we have a heater right here in the class, right? So, what will happen? The air above that will be heated and will start rising, because anything which is warmed up, the interstitial space between the particle will be less through expansion. They will expand, and because of expansion, per unit weight will be decreased, and that will create a low pressure area, right, as compared to the surrounding area. So, above the heater, a low pressure area will be generated. Once the air starts expanding, they are relatively warmer. Warmer means lighter, so they will start moving upward, right? This is how it will take place. The moment they are moving upward, a low pressure area is created, so the air from the surrounding area will come to fill that gap, right? That is a common phenomenon we all have experienced. So, look at here, in the low pressure area, air will always rise, can we say that? And there will be convergence.
Convergence of surrounding
Surrounding area.
So there will only be vertical expansion, or there will be horizontal also?
Just think about it, whether it will be there or not. Let's say, suppose a question has arisen in your mind. Let's say, suppose this is a low pressure area. So, we have already understood that there will be vertical movement of air. Now, when you are talking about the horizontal, is it possible? When we are talking about horizontal, that means air will move from low to high, because this area, surrounding area, is high pressure. So, that will defy the pressure gradient, which is not possible. That means water cannot move from the lower height to greater height naturally, at least, unless until you give a lot of energy. So, reverse gravity against the gravity movement of water is not possible. So, similar principle will be applied here also. Just like gravity plays its role from high to low, similarly the air will also move from high to low area, right? Horizontal expansion is not possible, so vertical rise. So, when we talk about low pressure, can we say that low pressure is the area of convergence and the area of rise of air? Rise of air, sometimes it is called convection if it is vertically rising. There may not be a perfect vertical rise, so we'll not call it convection, right? So these three are common and complementary to each other. Remember one thing, wherever one aspect is available, another will automatically follow. For example, if there is rise of air, there will be low pressure and there will be convergence. If there is convergence, there will be rise of air and there will be low pressure. If there is low pressure, there will be rise of air, there will be convergence. So all these three are complementary to each other. So this will be very handy in explaining the formation of subpolar low pressure belt, the formation of subtropical high pressure belt. Please, once we understand this area, this aspect, that all these three are complementary to each other. Even one aspect, the rest of the two will be induced naturally. Similarly, when we look at high pressure area, so high pressure areas are areas of divergence and areas of subsidence. This situation is called cyclogenesis or cyclonic situation. This is always produce an anticyclonic situation. Why I'm calling it cyclonic situation and anticyclonic situation, basically because all the low pressure area may not get transformed into a cyclone, but all the cyclones will always be associated with low pressure. All the anticyclones will always be associated with high pressure, though all the high pressure may not get transformed into anticyclone. In another word, we can say that all the low pressure areas are basically the areas of cyclones. All the high pressure areas are areas of anticyclone. Right? Now, let's assume that, for example, in that case of heater, we have a centralized really small heater. Let's say suppose in the middle of the class, from there till here, we have continuously a provision to heat up the air. Let's say heater, 2 feet broad, heater is there all along the central part of class. We can correlate it with the equatorial region, right? So air in the middle of the class will be heated and will start rising, right? It will rise up to where? It will start rising. कहाँ तक जाएगी ये? हंसने ही वाली बात है. ट्रोपोस्फेयर तक. जब तक ठंडी नहीं होगी तब तक कहाँ तक ठंडी नहीं होगी? ट्रोपोस्फेयर तक जाएगी. ये क्लास में उठ रही है एयर, सीलिंग तक जाएगी ना? नहीं. तो ये यूपीएससी का भी यही चक्कर है. हम ओपन एंडेड सोचते हैं, इसको क्लोज करके सोचो. अब when you have in the central part a heater is kept, now the air which is rising will be rising along the marginal part in the middle, right, and hit the ceiling. What will happen at the ceiling? Divergence, right? Divergence is the zone of high pressure, right? That's what we have read. This diverging air will hit the wall, both the sides, and now along the wall they'll sink, right? Along the wall they'll sink. That sinking air will produce
Low pressure.
high pressure, right? Because when the air is sinking, not only the air particles are increasing on the ground, but also it is forcing some exerting pressure because of the dynamism, because of the subsidence, because of the movement, right? So we put extra pressure on the ground. We'll put extra amount of air particles on the ground, right? So that will automatically generate a high pressure area. So that high pressure area and then a low pressure area. So a cellular motion of air will begin, right? This cell will begin. Now this is a low pressure area. So low pressure area, both the sides you have high pressure area. So can we say that on the ground, every low pressure area has to be surrounded from all sides by high pressure area, right? Both the sides at least. And now not only this side, on the top also it has to be high pressure area, right? Because if you choke that divergence, gradually the pressure will increase downward and the air will not be able to rise.
Sir, if there is a duct, you can say duct from down to roof, then what will
the same will happen if you choke the duct, the mouth of the duct on the top. Just like the simplest possible example can be when you are planting water in a garden, right? You have a pipe in your hand. That pipe is connected with the tape. The tape is connected with the tank, right? If you choke the mouth of pipe, what will happen? Mouth is outflow, right? That is a high pressure area for the rest of the area. And for this, tape is a high pressure area. For that tape, tank is the high pressure area. So there is a connectivity of the system. The whole system is connected, interlinked. The moment you choke it, even if tape is open, tank is open, the water will not flow. The whole system will be blocked. And the pressure will increase upward. That's why very often the pipe will come out of the tape, right? Because you have blocked here. So if you choke this, the entire system will be blocked. So if you choke this, the entire system will be blocked, right? So can we say that for any low pressure on the ground, there must be a high pressure in the upper air? For any low pressure on the ground, there must be a high pressure higher up. In the atmosphere, right? Otherwise, low pressure will not be able to sustain. That means for any cyclone, there must be an anticyclone, not only on the ground, but also in the upper air. These are fundamental principles when we discuss about the atmospheric circulation. That means for any inflow to continue, there must be an outflow. Any doubt? Hopefully we are clear. If any point or any component of the system is disturbed, rest of the system will be affected. Right? This is the general flow of the atmosphere. For cyclone is what? Low pressure area. A very specialized low pressure is called cyclone. When the wind velocity is more than 30-35 kilometers, that's called cyclone. Right? So cyclone is a special category low pressure center, we can say that. Anticyclone is a special category high pressure center. So for any low pressure, there is a need of high pressure in the upper air. That means for any cyclone on the ground, there must be an anticyclone in the upper air. High pressure areas are anticyclonic. So if you want a cyclone here, it must be surrounded from all sides by an anticyclone. Right? So for any cyclonic circulation, there must be anticyclonic circulation around. Are we clear? Just before I go to the pressure system, let's talk about wind also. A bit of wind, brief of wind. What is wind? Moving, very gentle movement of air.
Movement of air from
High pressure to low pressure area will be wind. And if it is from low pressure to high pressure area, then is it possible that there will be a direction of low pressure to high pressure? What was this? What was this when the air is rising? On the ground you have low pressure, this is high pressure. Is it so? Is that high pressure really a high pressure? And if it is a high pressure, in what context? It is a permanent one. If you want this permanent flow, that has to be permanent, this has to be permanent. That is a high pressure in its horizontal context. This high pressure is not high pressure for this ground pressure. For this ground pressure, this is a high pressure and that is a low pressure. That's why air is flowing. And for that high pressure, when we are talking about divergence along the ceiling, that high pressure is as compared to the surrounding area in terms of horizontal component, because ceiling there will be a good amount of accumulation of air, and that accumulated air will generate extra quantity of air there as compared to the surrounding area along the ceiling. So that high pressure, when we are talking about on the upper area, it is a high pressure with respect to its horizontal direction or the area horizontally there, right? So first, air moves under the influence of pressure gradient force, right? Now the movement of air may be in horizontal direction, whether it is on the ground or in the upper air, or the movement may be vertical in nature. The horizontally moving air is called wind. Horizontally moving air, whether it is on the ground or in the upper air, only the horizontally moving air is called wind. When the air moves in a vertical direction, we call it air current. So air current is air moving in vertical direction. Air current may be updraft or downdraft. That means downward moving or upward moving. Updraft is what we call convective current. That's why you will never hear convective wind. You'll never use the term convective wind. It will always be convective current. This will be subsiding current. This will be subsiding current. That means this is a characteristics of low pressure, again we can correlate, and this is high pressure areas. Any doubt? So low pressure area convection convergence will be synonymous. High pressure area subsidence and divergence will be synonymous. Like in this case, when the air was coming down from the ceiling to along the wall on the ground. So if you remove the wall, then air will flow in both the direction, because that high pressure will be a high pressure pocket as compared to all areas. So the air will diverge in both the direction. So that's what it is, divergent. In the closed room, it will be a single way divergence. So it will not single way movement. So they not necessarily a divergence. Divergence will be only there. Wind on the basis of speed is classified into breeze, wind, and stream. Breeze is slow moving wind. Wind is normal speed. Normal speed of the wind is roughly around 8 to 10 km per hour. That means when it is less than that, 8 kilometer per hour, or when it is more than that, when it is more than 8 kilometer per hour. We call it a stream. Land breeze, sea breeze, right? Jet stream, right? So the term, all these terms are basically associated with wind, horizontally moving. When we say jet stream, that means they are horizontally moving, but with a very high velocity. When we are saying land breeze, that means it is horizontally moving with a very slow speed, right?
आपने बोला कि अगर बॉल नहीं होगा तो जो एयर है वो बस चलती रहेगी, नीचे सबसाइड नहीं करेगी।
सबसाइड करेगी कहीं ना कहीं से, तो इसका गो डाउन होगा ना। ये लो प्रेशर, हम एटमॉस्फेयर में जब आएंगे तो इसी एग्जांपल को हम एक्सटेंड करेंगे। एटमॉस्फेयर इज नॉट एज क्लोज एज द सीलिंग, yet they behave like that. When the air is rising, it will rise up till where somewhere, then somehow they have to stop. So that will be very much similar to ceiling example. That ceiling is tropopause. That's what we demarcate tropopause at the end of troposphere.
So is there any issue of like energy or intensity of air particles at which distance they are moving upward?
Yeah, definitely. That will be determined by the force on the ground. If we are sending something, we are throwing something, the distance covered by that particle will be determined by the energy you have put into it. So if the heating is intense, obviously the distance covered will be more. A very good example is exhaust. What does exhaust do? You put exhaust in a corner and you imagine that there will be fresh air coming into it. So first thing that it has to remove the older air from the room. So how it is expected to pull the air from that corner of the room? It doesn't have any hand. आओ तुम भी आ जाओ types. ऐसा तो है नहीं, right? It has to create something, some system. So what does it do? Creates low pressure. The fan does only one thing, that it throws out the air nearby it. That's it. Its work is done. So the moment air near the गाना सुन रहे हो? अच्छा, आवाज कहाँ से आ रही? The moment air near the fan is removed, so low pressure is created. So that the moment low pressure is created, air nearby will be rushed. That's why exhaust will not be functioning unless it is properly packed, right? Because it has sent, so that it will come return and there will be immediate circulation. So you'll have to pack it properly so that the outside air doesn't fill that gap created by the fan. So the moment that air is removed by the exhaust, a low pressure is created, and the low pressure is the general tendency of the fluid. The air will start moving and covering that low pressure area. Now look at how it is functioning with the example of exhaust itself. आप छोटा exhaust washroom में लगाते हो, but अगर कमरे में लगाना हो तो इतना छोटा exhaust कुछ काम करेगा?
Small area. Depends on area जहाँ पे air suck करनी है.
उसका catchment area का limitation होगा अपना. If the exhaust is very small, its catchment area will be small. If exhaust is very big, its catchment area will.
We have 4 fans in the room. बड़ा रूम में तो एक फैन से काम नहीं चलेगा.
नहीं चलेगा, तो वो तो सप्लाई करना है, वो दूसरी चीज है. फैन दूसरी चीज है, एग्जॉस्ट दूसरी चीज. जब आप सक करना चाहते हैं एयर को, when you want to pump it out, when you want the entire room air, for a small exhaust in this classroom, will definitely not be non-functional. It is as good as not having it, right? Why? Because the intensity generated by that exhaust will not be sufficient catchment area, will not be having or will not be covering the entire classroom. So for that you have to have bigger. So what does the size of exhaust do? It increases the intensity of low pressure, right? That means it increases the intensity of pressure gradient force. Let's come back to pressure gradient force. It is a force generated because of the gradient in pressure system of the adjacent area. You can write down pressure gradient force is the force generated. Pressure gradient force is the force generated because of the difference of pressure in the adjacent area. Is the force generated because of the difference in the pressure of adjacent area which is fundamental for the movement of air. Which is fundamental for the movement of air. It also affects the velocity of the air and the volume of the air reaching in a low pressure area. Volume of the air reaching towards the low pressure area as it delineates the catchment area. As it delineates the catchment area of a low pressure system. Of a low pressure system. The direction of the pressure gradient force is perpendicular to isobars. The direction of the pressure gradient force is always perpendicular to the isobars. ब्रैकेट में लिख लीजिए isobars are imaginary line joining pressure have equal pressure. Isobars are imaginary line joining places having equal pressure. Consequently, the primary direction of wind is perpendicular to the isobars. Primary direction of the wind is perpendicular to the isobars.
Primary direction
of the wind is perpendicular to the isobars. However, the actual direction on the ground is different because of other factors. Actual direction is different. However, the actual direction, the real direction on the ground is different because of other factors affecting the direction of the wind, like Coriolis force, frictional force, etc. Right? Pressure gradient force, wind velocity is directly proportional to PGF. Now, if the intensity of PGF is basically very high at the low pressure, just like exhaust, if the exhaust is bigger, it can cover larger area. So, the moment intensity of low pressure is much high, so what will happen? Its catchment area will be much bigger. So, it can attract air from far away distance. Right? So, if the catchment area is bigger, so obviously the air particle, volume of air, the quantity of air reaching into that area will definitely be higher. Clear? Now, pressure builds over the Earth's surface.
and ये pressure gradient perpendicular isobars कैसे होगा?
कॉन्टूर समझते हो? कॉन्टूर Contour means, contour is just like imaginary line joining places having equal height. जब हम ऐसे स्लोप बनाते हैं तो ऐसे ऐसे contour बनेगा. Like if we take height of 100 meters. So if it is 100 meters, so this line will be 100 meters. This line will be 90 meters, 80 meters and so on. If the water flow direction we are supposed to look, so water will flow perpendicular to the contours. Let's draw an isobar because it is very visible. We can see it, so we can easily experience it and understand it. In the case of pressure, we'll have to imagine because we can't see it. That's where we have problem. Now let's suppose this is a high pressure area, then this is a low pressure area, right? Low pressure line. In between we have, it will be decreasing, right? The value of the pressure will keep on decreasing. So what will be the direction of the wind? Like this. So why it is so? Because this is the direction of the pressure gradient force, right? So if pressure gradient force is the only factor, suppose in preliminary examination, the question is asked, if pressure gradient force is the only force in affecting the direction and the movement of air or wind, wind will always blow perpendicular to the isobars. It will always blow like this because this is the direction of the pressure gradient force. Directly proportional. इन्वर्सली लिखा दिया क्या? नहीं, देख लो तो चेक करो. Wind velocity is directly proportional or inversely proportional? प्रेशर ग्रेडियंट फोर्स के बारे में जब अभी लिख रहे थे हम लोग, नहीं डायरेक्टली लिखा है. Pressure belts are over the earth's surface, right? We know that there are how many pressure belts? No idea? Very good. An empty bottle always have greater capacity to take. So don't worry about that. Now, how many pressure belts are there? If you look at, there are 7 pressure belts on the ground. Equatorial, low pressure, roughly around 5 degree north to 5 degree south. That's what we have already talked about, the regional distribution of pressure, equatorial region, subtropical region. Then we have subtropical high pressure belt. Roughly around 25 to 35 degree north and south both. Then we have subpolar low pressure belt. Roughly around 55 degree to 65 degree north south. Then we have polar high pressure belts. Polar high pressure around the pole, both North Pole and South Pole. So look at 2, 2, 4, 2, 6 and 1 common to both the hemisphere. That is 7 pressure belts on the surface of the earth. Now, why is it so difficult to explain? It is really difficult to explain the entire pressure system. Scientists have consumed a lot of energy and have taken a lot of time ultimately to explain all the pressure belts. Because you look at here, what we have discussed is pressure temperature relationship. So high temperature will produce low pressure and low temperature will produce high pressure. Now equatorial region is the region having high temperature, so can be easily explained. High temperature, low pressure. Polar region, low temperature, So obviously air get compressed and all. It occupies lesser area, so weight per unit area will be more. So low temperature, high pressure. Now the fundamental difficulty is in explaining this only, these two. Because how you will explain the subtropical high pressure, a high pressure area in relatively higher temperature and a low pressure area in relatively lower temperature. When we generally assume the existence of temperature or distribution of temperature from equator towards the pole, in general it decreases. There are exceptional reasons for that. But if you move on the continent, obviously it will decrease. If you move on the ocean, it will definitely decrease. On the continent's height and all may have some impact, right? So now look at here, 30 to 35 degree latitude is definitely warmer as compared to 55 to 60 degree latitude. So now this creates lot of contradictions and increases the complexity in explaining the pressure belts. Until very recently, it was not properly explained, right? Last 200, 300 years, it was not explained. Most of the observed pattern we are finding 7 pressure belts, and scientists could explain only 3 pressure belts. So it was very handy for them later on, which scientists came up with some different. That's why Headley's remembered far more than any other person. That's why you hear very often Headley's solenoid, right? How it will be generated. So now the earliest belief was the existence of 3 pressure belts. Especially Greeks have explained the existence of 3 pressure belts, and those 3 pressure belts were equatorial low pressure belt, and 2 polar high pressure belt. These 3 are called thermally induced pressure belts. Thermally induced pressure belts. It was very easy to explain, but later on when observed pattern found that there are 7 pressure belts, then they started explaining. So these pressure belts are basically true about on a static Earth. When Earth is not dynamic, that means Earth is not rotating, or the influence of rotation is not there. On a static Earth, you can easily explain these 3 pressure belts. Just though I'll be writing or making diagram in 2-dimensional, you have to imagine in 3-dimensional diagram. Let's say, suppose this is a polar region, North Pole, South Pole, and this is equatorial region. So we can easily explain, let's say suppose equatorial region 5 degree north to 5 degree south. So what will happen, this area is definitely experiencing high heat. So overall high temperature, right? High temperature resulting into expansion of air, and this will result into rise of air, ultimately making a low pressure area. Okay. Now when the air is rising here, we can easily explain why the air should rise and why there will be a low pressure area here. Similarly, if you look at this polar region, low temperature, compression of air, right? Subsidence along it, and high pressure. Right? So very easy to explain both these high pressure area and this single low pressure area, which is common to both the hemisphere. Now, whatever is moving away from the equator has to come back, right? Because it is not, in that particular sense, it is a closed system, because no new air will be created each and every now and then on every daily basis, and that air will be moving and then can go to meet the creator. They have to come back because equatorial region is not producing, there is no machine to produce air there. So it is the same air which has to travel and somehow come back, right? So obviously the moment there is rise, there is convergence, that is but natural. Now the question arises whether this convergence is from here or from somewhere in the middle. So let's see what happens to the rising air. When the air starts rising, there will be cooling of air, right? Why?
Either 1 degree pressure decreases every 1 kilometer or 6.5 degrees Celsius.
So what that has to do with the rising air? Is it because of environmental lapse rate? Environmental lapse rate produces
The energy which provides air to rise, moving with heights decreases.
Once it has given that, so energy will be intact. Why there should be a change in energy? Just
It is dissipated in surroundings.
so once it flows in the surrounding horizontal direction, only then it should decrease the temperature
Its energy is dissipated.
in the surroundings. That's why I gave you example when we are discussing about temperature. So environmental lapse rate is there, but environmental lapse will not be responsible for decrease in temperature.
So because the 6.5 here is 6.5 degree Celsius less than my humidity.
Fine, let's assume that at ground the temperature is 40 degrees Celsius, air is rising, here it is say 34.5 degrees Celsius, the normal rate. So do you expect here it is 40 and the air temperature here will be 34.5? It will be much lesser, or much higher may be possible, depending upon that, depending on the speed of the wind. Now, hope you remember first thing, that intensity of heat requires certain duration, जिसको acclimatization, to transfer itself into equivalent temperature, right? When you remove it fast, it will not have its impact. When the air is rising, it is rising at a much faster velocity. So first thing is that the rising air cools adiabatically, not diabatically. Remember, rising air will definitely cool down, will definitely experience lowering of temperature, but the dominant process will be adiabatic, not diabetic. So it will experience adiabatic cooling, and the subsiding one will experience adiabatic heating, not environmental lapse rate. Because of that, a minor impact might be there, but fundamentally the cooling of rising air will be associated with adiabatic cooling, not diabetic cooling. Remember this thing. Fine, but what are reason it will be cooling? That is a compulsory consequence.
So because it is due to volume change. Volume of
Air which is rising, it will expand. Automatically it will expand horizontally also. It will cover larger area. So volume will increase. So same amount of energy will be distributed on a larger surface. So automatically their energy will decrease. Right? So when it is experiencing decrease in temperature means heavier. When the temperature decreases, anything, if you experience decrease in temperature, that becomes cooler, and cooler objects are heavier as compared to the direct, right? So when they are cooling, they will become heavier. So after a point of time, heavier, and at a particular height in the atmosphere, it will be too heavy to rise upward wherever it takes place. When it is rising, after a point of layer in the atmosphere, there will be too heavy to rise further. So now only two options, either you diverge there or you come down, right? Now coming down is not possible, basically because of the buoyancy, because the air which is rising, if air stops rising, then they may come down. But since air is continuously rising, and that is basically fueling the rise of air. So wherever it is there, the only one option left now is diverge. So our example of sealing is similar here in all respect except one thing. That in the case of example of the glass, not a single air particle can cross sealing. Right? And it's a relatively thin line, a very small system. In the case of atmosphere, that is exactly like a sealing, but in a three-dimensional manner. The air first will have horizontal component with three-dimensional aspect, width, length, and height. So maybe a thick layer of air is diverging, so they are diverging like this, they are diverging like this, and a percentage of air may be able to move further as well. But 90-95% of the air will diverge in a particular layer of the atmosphere.
It will diverge in every layer, मतलब जहाँ पर भी temperature down हो रहा है air का, तो वो हर जगह diverge होता है, तो बचेगी फिर पर फिर diverge
नहीं, वो हर कोई वहीं पे डाइवर्ज होगी, unless and until there is a scope of re-energizing the air. Re-energizing the air means if the temperature is increased somehow, right? So the outer boundary of that, up till where the air normally, the air which has started moving from the surface can reach, is the outer boundary of first layer of the atmosphere, troposphere, and that is called tropopause, pausing of troposphere, ending of troposphere. And that's why most of the atmospheric phenomena is confined to troposphere. Right? There is rare phenomena beyond the troposphere, especially related to atmosphere. So कुछ तो जा ही सकती है, नहीं भी जा सकती है तो भेज देंगे इसको, ऐसा क्या, पंप लगा देंगे. जा सकती तो बहुत, हम लोग तो काफी कैपेबल है, चाइनीज की तरह 4-5 मिसाइल छोड़ देंगे वहां पे. सपोज करो अगर मिसाइल छोड़ दिए, जैसे आर्टिफिशियल रेन करवाया था उसने, रोका था उसको, रेन को रोक दिया था उसने. अब इमेजिन करो हम लोग जब पटाखे फोड़ते हैं तो क्या असर होता होगा, हम लोग जब मिसाइल छोड़ते हैं, कोई भी मिसाइल छोड़ता है, हम लोग का मतलब पूरा ह्यूमन की बात कर रहा हूँ, ह्यूमंस जब मिसाइल छोड़ेंगे तो क्या असर होगा, डेफिनेटली असर होगा. इसको हम कोरिलेट करेंगे रेनफॉल पे, पॉल्यूशन पे, hygroscopic particles पे. So if there is some mechanism, natural mechanism or artificial mechanism which can re-energize the air, so air will definitely travel at a greater height, right? That's why troposphere over the equator is thicker and over the pole it is thinner. The height of troposphere at the equator is 16 km and height of the troposphere at pole is 8 km. There will be seasonal variation in the height of troposphere as well.
Summer season will be more.
Yes, thicker, and winter will be slightly cool. Sink कर जाएगा वो. Temperature ज़्यादा होगा तो उसकी energy ज़्यादा होगी, energy ज़्यादा हुई तो expansion ज़्यादा हो. So automatically that will expand more, right? So here.
हमने फर्स्ट क्लास में डिस्कस किया था कि एटमॉस्फेयर तो हर जगह बराबर ही है, तो ऐसे नहीं है फिर. अगर ट्रोपोस्फेयर इक्वेटर पे ज्यादा है,
एटमॉस्फेयर और ट्रोपोस्फेयर में क्या फर्क है? हाँ. अब ज्योति पूरी है, उसका हाथ एक कंपोनेंट है, राइट? So when we talk about atmosphere, it has several layers. One component is troposphere. Troposphere, stratosphere. अभी तुम stratosphere बोले, तो हम पूरे layers को हम atmosphere, we call it atmosphere. All the layers above the earth surface, gaseous layer, is called atmosphere. When one component is the closest and nearest to the ground, and the first layer is called troposphere. Right now we are talking about troposphere. If troposphere is thicker here, the stratosphere will be thinner there. If over the pole troposphere is thinner, less thick, so the stratosphere will be more thick. So ultimately that circle will be completed as far as atmosphere is concerned. Now the air will diverge, right? And it was believed, now it is a high pressure area. Both the poles is experiencing high pressure area. So the air will definitely move towards polar equatorial region from both the sides. Air will definitely move. Now imagine three-dimensional figure, pole air is moving from this side also. If we take this example of pole, right? So pole is a high pressure area, air will be moving in all directions, right? So this is a circular area. So in this direction, every direction will be moving. It is automatic without any doubt. Now on a static earth, earlier what happened, scientists used to believe that there is nothing other than temperature as a factor which can affect whether it is produce or induce the pressure system, right? So they believe that the air which is diverging here and air which is diverging on the ground will complete the circulation. When it is diverging, it will be an area of subsidence as well, right? So that air which is being removed from the surface here, that has to be compensated from the air coming from top. So that's how a system will be joined together to form one cell in each hemisphere. That one cell in southern hemisphere, one cell in northern hemisphere. And that is what you call unicellular model of atmospheric circulation. Unicellular model of atmospheric circulation. Unicellular model of atmospheric circulation, right? Now, when we talk about unicellular model of atmospheric circulation, then it is single cell. So we can explain only three types of pressure belts, right? So later on, when it was found that two more pressure belts exist, one is subtropical high pressure belt, another one is subpolar, the scientists got disturbed, and it was very difficult for them to explain that, right? How these two pressure belts can be created, and that too in the higher temperature region there is a high pressure, in the lower temperature region there is a low pressure, which contradicts the basic principle of pressure temperature relationship, isn't it? The most, in any case, the most fundamental factor of pressure generation will always be temperature, right? So later on they started explaining, and that's where the scientists came to suggest that the role of dynamism of Earth over atmospheric circulation. Then they invented the force, Coriolis force. That's what we call Farrell's laws. Farrell's law, because he was the one who discovered it, and the term is Coriolis force. Right? It plays a very significant role as the second most important factor in producing pressure belts. Right? Now, how it is playing a role, we can easily understand. Now, most fundamental of the pressure system will always be equatorial low. Rise of air, then here subsidence, that will remain as it is. Now, what will happen in between will be determined by Coriolis force. How it will be determined? Just imagine this wall as equatorial region, right? Now, let's take just one hemisphere, northern hemisphere. So, what later on it was suggested that when the air which is rising and cools down adiabatically, after a point of time it will not be able to move further, thereafter it will diverge. Now, the divergence toward the pole in the unicellular model in a static Earth is supposed to be in a straight line and go and reach till the poles. That is perpendicular to the isobars. That is exactly in the direction of pressure gradient force.
सर आइसोबार के तो पैरेलल हो गई.
सर आइसोबार्स अर्थ पे वर्टिकल होते हैं हॉरिजॉन्टल होते हैं.
हॉरिजॉन्टल से ग्राउंड पे हम ड्रॉ करते हैं ना आइसोबार्स. थोड़ा सा एनसीईआरटी पढ़ लिया कीजिए तो चीजें ज्यादा मजेदार हो जाएंगी होपफुली. Now this is isobars when you have high pressure. So you can draw a line, the highest value pressure isobars and the lowest value isobars. So when the air is moving higher up in the atmosphere from the equator towards the pole, so what the unicellular model expects that it will move perpendicular to the isobars and reach there and descend till over the pole, and there will be circulation, right? Now then comes the role of Coriolis force, and it is suggested that, write down please, on a dynamic earth the Coriolis force causes deflection. On a dynamic earth, Coriolis force causes deflection of wind rightward in the northern hemisphere, and leftward in the southern hemisphere. The diverging air above the equator, moves towards the pole. However, it will not be able to reach the polar region because of Coriolis force. The deflection produced by Coriolis force will change its direction and after certain distance it blows parallel to the isobars. After certain distance it blows parallel to the isobars. Generally 30-degree latitude away from its rise. They are cooled further along the journey. And it starts piling up. Hence they descend and make a high pressure on the ground. This is called subtropical high pressure area. Paragraph change. On the ground, the subtropical high pressure area forms an area of divergence and the wind start moving both equatorward and poleward. Wind starts moving both equatorward and poleward. The equatorward component fills the equatorial low pressure belt. And the poleward component converges with the wind coming from polar high pressure. In and around subtropical latitude. This converging air masses produces a low pressure area. Air masses produces low pressure area. And is called subpolar low pressure area. This is how three cells are produced. In each hemisphere. And is popularly known as tricellular model. Hope you have read it. Now let's try to understand it. Just like this, we were talking about when the air is moving in this direction. Now if we expect that it to move and travel in a straight direction perpendicular to the isobars, it will definitely be able to reach up till the pole. Now the air which has cooled down, and because of heavy weight it has diverged. Now it is moving in a horizontal direction in a particular layer of the atmosphere where it is supposed to acclimatize with the temperature of that layer. Here there will be a diabatic change of temperature. So it will become further heavy. Hope you are getting that. Now when we expect that it to move straight in a straight path, it may reach pole. Now let's apply Coriolis force. So it will turn rightward. So after a point of time, it will be almost perpendicular over the surface along the isobars. It will not be able to reach up till the pole. Now imagine that piled up of air doesn't have any option but to sink. Right? So the moment it is sinking, subsiding air currents will be generated, and that sinking subsiding air current will produce a high pressure on the ground. Right? In this example of diagram, we can make that. When it is rising over the equatorial region, it is diverging somewhere here, and ultimately it will sink somewhere in the middle of the latitude itself. It will not be able to reach up till the pole. The moment it is divergence, the divergence will be both the sides on the ground. An automatic already explained high pressure area here exists. So it will automatically supply air. So somewhere in the middle they will converge. And converge and rise. That's why we have discussed that the low pressure area, convergence and rise of air is complementary to each other. To understand this part only. So it will move similar way and descend here and it will join it here. So that's how you look at each hemisphere. This is equatorial region, 0 degree. Now this is subtropical high pressure belt. This is subpolar low pressure belt and this is polar high pressure belt. So in each hemisphere, 1, 2, 3 cells will be formed and we call it tricellular model. So that is how 7 pressure belts can be explained. These 2 and 2 on other side, 4 pressure belts are called dynamically induced pressure belts. And the first 3 are called thermal belts or thermally induced pressure belts. So equatorial low will be also called thermal low. Polar high will also be called thermal high. The moment we are talking about thermal high means we are talking about polar high pressure. If we are talking about dynamic low, that means subpolar low pressure. If we are talking about dynamic high, that means subtropical high pressure belt. Write down please. The difference in the thermal highs and dynamic highs, the difference in the thermal highs and dynamic highs is associated with the difference in the thermal highs and dynamic highs is associated with its mode of origin. The difference in between the thermal highs and dynamic highs is associated with the mode of its origin. Polar high pressures are produced because of temperature. Polar high pressures are produced because of temperature. Here, high pressure is the cause. High pressure is the cause, whereas subsidence and divergence are the result, effect. Whereas the subsidence and divergence are the effect. Subtropical highs are produced because of Coriolis force. Here, subsidence is the fundamental cause. And high pressure and divergence are effects. High pressure and divergence are effects. Similarly, low pressure is the cause in the equatorial region. Low pressure is the cause in equatorial region. Convergence and rise of air is the effect. but in the subpolar low pressure belt, convergence is the cause, convergence is the cause, and low pressure and rise of air are the effects. Paragraph change. The idealized pressure system on the surface of the earth. The real pressure belts on the surface of the earth. Ideally, we have 7 pressure belts. Which are permanent and continuous in their respective regions. However, in reality, they are very different and dynamic. Both temporally and spatially. They have hemispherical contrast, regional and intra-regional contrast. For example, the subtropical high pressure belt of northern hemisphere is weaker, discontinuous, and discontinuous as compared to their southern counterpart. During summer season, they are found only in the form of cells over the oceans. They are found only over the oceans in the form of cells. और जैसे भी लिखना है. They are found only over the oceans in the form of cells. For example, Azores High in Atlantic Ocean. Azores, A-Z-H-O-R-E. Azore. Azore is an island. Azores High in the Atlantic Ocean and Hawaiian High in the Pacific Ocean. Similarly, the subpolar low pressure belts are discontinued over the continents. Similarly, the subpolar low pressure belts are discontinuous over the continent and forms two cells over the oceans that is Icelandic low in Atlantic Ocean, Icelandic low in Atlantic Ocean, Icelandic low in Atlantic Ocean, and Aleutian low in Pacific Ocean, and Aleutian low in Pacific Ocean. Besides, there is a hemispherical variation. There is a hemispherical variation in the position of equatorial lows as well. In the position of equatorial lows as well. During northern hemisphere summer, its poleward shift is much higher and may reach up to 25° north along the Indian subcontinent, which may hardly be 10° south, which may hardly reach 10° south in the southern hemisphere summer, which may hardly reach 10° south in the southern hemisphere summer. Paragraph change. The pressure belts also experience a spatial variation along the longitudes. During summer season, the entire pressure system shifts northward, not northward, sorry, poleward. Entire pressure system shifts poleward, whereas during winter season, it moves equatorward, it shifts equatorward. The shift in the pressure belts is associated with various atmospheric consequences. The shift in the pressure belts is associated with various atmospheric consequences. Number 1, general location of origin and destination of primary winds. Origin and destination of primary winds. Second, change in the location of cyclones. Third, It produces secondary wind of regional magnitude, called monsoon. Fourth, it produces two wind system in between 30 to 45 degree north and 30 to 40 degree south latitude. In this belt, presence of two wind in different seasons, with their different direction, produces two unique climatic types. Two unique climatic types. Mediterranean climate which experiences dry summer and wet winter, and China type with rainfall throughout the year, Next point, it produces a semi-arid steppe climate. Semi-arid steppe climate along the poleward side of the subtropical high pressure belt. That's where we finish pressure system.